In this presentation, I want to share a few thoughts about the Semester 1 exam from 2013-2014 school year. So let's take a look at the first of the free response questions. Water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at the rate of the square root of t plus 1 gallons per minute for times between 0 and 120 minutes. At time t equals 0, the tank contains 30 gallons of water. The first question asks how many gallons of water leak out of the tank from time t equals 0 to t equals 3 minutes. Now there is a math fact going on behind the scenes here, a couple of them really for this problem. The first one is that if you integrate a rate, you get an accumulation of the quantity in the rate. In this case, an accumulation of gallons. The second math fact is the fundamental theorem of calculus, and we'll use that to evaluate the integral in this part A. So there is a rate of square root of t plus 1 gallons per minute, and that's the thing that we're going to integrate. So we write an integral of that. So that's our integrand, that same function, and we've got there the limits of integration from 0 minutes to 3 minutes. Note the dt. That's an important part of the integral expression. It formally ends the integral. You get 1 point for the integrand and 1 point for the limits of integration. Now it's time to try to evaluate this to figure out how many gallons of water leak out. So for this, what we're going to do is consider that integrand as an exponential equation. Now we're going to integrate an exponential function. What we'd like to do in these cases is increase that exponent by 1, then divide by the new exponent. Then we're going to evaluate that between 0 and 3, which means we'll plug 3 into that expression first, then we'll plug 0 in and subtract those two results. This is what it looks like, and that right there is a perfectly acceptable answer for this question. Many students who took this test in the year 2013-2014 had difficulty with the rational exponents. That's a pre-calculus topic. If everything goes really well and you're able to evaluate this, you get 14 over 3. But like I said before, it's not important to have it as 14 over 3, as long as you've got it written in such a way that the only thing that stands between us and the numerical answer is arithmetic, then you're good to go. So that long looking expression in the middle of the bottom of the screen there, that's perfectly fine for an answer. Either one of those will do just fine. For the next part of this problem, we have to figure out how many gallons of water are in the tank at time t equals 3 minutes. There are 3 factors affecting how much water is in the tank at a particular moment in time. Those 3 factors are how much water we started with, how much we've added, and how much has leaked out. So the situation is this. We've got a tank. It's underground, and water is going in at a constant rate. But look, there's a crack developing in the tank. So some water is leaking out. Oh no. Let's look at this vessel as if it were a cup. When we read the problem, we see that at time t equals 0, the tank contains already 30 gallons of water. So I'll put a mark up there at 30 gallons. Now, water is being added at a constant rate of 8 gallons per minute for a grand total of 3 minutes. So doing some quick arithmetic here, that means that in the 3 minutes, 24 gallons are added. So that brings our total up to 54 gallons at time t equals 3. But we also have to factor in how much has leaked out. So from this 54 gallons, we'll subtract the amount that leaked out And we had previously shown that that was 14/3 gallons. That's a perfectly acceptable way to present the answer. Or 40 1/3 gallons is okay too. Moving on to question 2 for part A. We are given a curve defined by an implicitly defined function. This, in fact, is y as a function of x, although it would be really, really hard for us to solve this for y. Even so, we're able to use implicit differentiation to show that the derivative is equal to this particular expression that we've been offered. The way we're going to do it is we're going to differentiate both sides of the equation that we were given, and as we do, we'll take these one term at a time. The first term is 2y cubed. So if we want to differentiate 2y cubed, we realize first of all that the derivative of 2y cubed with respect to y is simply 6y squared. But here we want the derivative with respect to x, so we're going to treat y as a function of x. That means we've got an inside function y, so we'll need to multiply by the derivative of y with respect to x. So just handling that first term contributes just one little bit to the result after differentiating both sides of this equation. On to the next term here, we see we've got a constant times x squared times y. So the first thing we'll do is factor out that constant and then realize that we've got to multiply by the derivative of what follows. What follows is a product of two functions, x squared and y. So for this little bit, we're going to be using the product rule. You'll recall that the product rule says take the derivative of the first function times the second function plus the first function times the derivative of the second function. So we'll distribute that 6 to these two terms inside the brackets, and we'll get two new terms for the result after differentiating both sides of this equation. And now it's on to the next term. Well, the next term is minus 12x squared. Since it only has the variable x in it, differentiating this with respect to x offers no surprises and no difficulty. It's negative 24x. Moving on to the last term on the left-hand side, we see that we've got 6y. So the derivative of 6y is just 6 if we're differentiating with respect to y, but we're not. So we need to multiply that 6 by the derivative of y with respect to x. For the next part here, we're going to pay attention to the fact that we are taking a derivative on both sides of an equation. Many students neglected the right side of the equation and didn't pay any attention to that equals 1. Well, we need to take the derivative of that right-hand side, and of course the derivative of any constant is just 0. So when you differentiate an equation, you get a new equation. That might seem like a small detail, but oftentimes it's little things that make a big difference. Consider this non-mathematical example. Wow. I don't know if it was your grandma or my grandma or just whose grandma that was, but let's face it, punctuation saves lives. And now back to the calculus. So we had taken the derivative of both sides of this equation and gotten this amazing result. That's worth a point. The next thing we want to do is collect the 3 dy terms on one side of the equation. And as we do this, we realize that we have an opportunity to divide everything by 6 first. 6 is a common factor of all the terms in this problem. So now what we're going to do is rearrange the terms in such a way that we get all the terms that have dy dx, and there are 3 of them, on the left-hand side. And on the right-hand side, we have 4x minus 2xy. Carrying that over to the next slide here, we can see that it's possible to factor out a dy dx for these 3 terms. Then it's merely a matter of dividing both sides by that expression in the parentheses, and we just did what we were asked to do. Verify that dy dx is equal to this particular expression. The next part of this problem asks us to write an equation of each horizontal tangent line to the curve. Now, this part of the problem did not go particularly well for the students who took the exam in 2013-2014. It's possible that they became confused by the meaning of the derivative. The math fact that we need to keep in mind is that the slope of a horizontal tangent line is 0. Now, we were given the derivative or the slope of the tangent line in the beginning of the problem, so all we need to do here is set that equal to 0 and see what happens. So you get a point for setting this derivative equal to 0, and no students in the year 2013-2014 made progress beyond this point. Hey, look at that fraction. The only way that that fraction is going to be equal to 0 is if the top of the fraction is equal to 0. So we know that 4x minus 2xy must be equal to 0. Factoring that, we can observe that 2x times the quantity 2 minus y must be equal to 0. The only way you can have a product of 2 or more things equal 0 is if one of those things is equal to 0. So from here, we're going to break it into 2 possibilities. Either that first factor, 2x, is equal to 0, or the second factor, 2 minus y, is equal to 0. We'll investigate the first case first. That is, suppose 2x is equal to 0. That would mean that x is equal to 0. Now, again, we're looking for the equation of a horizontal tangent line. X equals 0, of course, is not an equation of any horizontal line, but rather a vertical line. But in this context, x equals 0 simply says on the original curve, at x equals 0 is where we might expect to see a horizontal tangent line. Of course, to know the equation for that tangent line, we'll also need to know the y coordinate. So the original equation was this, but if we replace the x with a 0, it becomes that. And that simplifies very nicely. And one of the things we're expected to be able to do on the advanced placement exam is we're expected to be able to solve equations like this using our calculator. So we'll get out our calculator and solve this equation and find out that y is equal to 0.165 and some change at this point when x is equal to 0. That means there's an ordered pair 0, 0.165 somewhere on the curve. And that's a location of a tangent point, or a point of tangency for a horizontal tangent line. Now, the curve that has this equation looks like this in the red, and I've sketched in that horizontal tangent at the ordered pair 0, 165. So that's what the tangent line looks like. We have another case to check out here, and that is case 2. What if 2 minus y is equal to 0? Well, the only way that could happen is if y were equal to 0. So we just need to verify that there's a place on this curve where y is equal to 2. The original equation looked like this, but replacing the y's with 2's gives us this equation, which simplifies to x squared equals negative 27 over 8. Now this equation, friends, doesn't have any solutions, so that means that y can't be equal to 2. And that second case that we were investigating doesn't lead to any horizontal tangent lines. Graphically, this looks like, again, this is what the original equation looks like. Graphically, what we get at y equals 2 is an asymptote. That is to say, the curve approaches this line, but it never reaches the height when y is equal to 2. Thus, we can't say there's a point of contact between the line y equals 2 and this curve anywhere. So our candidate y equals 2 as a horizontal tangent line is not, in fact, a horizontal tangent line at all. So just one answer for that last question.